All right, well, welcome everyone to the first session of Atmosphere, Ocean, and Climate Dynamics here at the CMOS Congress. The session is co-organized by Mark Stasna, Mike Waite, Ron McTaggart-Cowan, and me, Adam Monahan. So I'm joining you now from Victoria in the traditional territories of the Algonquin-speaking peoples in the Esquimalt, Songhees, and Wasanich nations. And our session today is ably assisted by Jiahui Zhao. The way things are going to work is we are going to have a set of 3 talks, followed by a brief presentation of one of the posters in our session, followed then by a set of 3 more talks. So the whole session will be 1 hour and 40 minutes in duration. If you do have any questions, I'll ask you to indicate that in the chat. So you can either type your question in the chat or just indicate that you'd like to ask one, and I'll invite you when the time is right to ask your question. So we're a couple minutes before noon here by my time. Any of the other co-organizers, would you like to say anything before we get going?
Just say hi. It's great to be all together again, and you know, maybe we'll do it again in person next year. But it's been good the last couple of years with virtual that a lot of people can join. I think it's a session I look forward to all the time, and I'm looking forward to seeing the talks.
Absolutely. All right then. Well, why don't we get going then? I'd like to invite Alain Javet, our first speaker, to talk to us about transmission reflection of 3-dimensional internal gravity waves, or gravity wave packets, rather. So please.
All right, thank you very much for that wonderful introduction. And thank you all for being here to open the session with me. To refresh anyone's memory, in case you haven't looked at waves in a while, internal gravity waves are horizontally and vertically propagating perturbations or disturbances to surfaces of constant effective density in a stably stratified fluid. For the well, they exist on a range of spatial and temporal scales, and for the geophysical applications that a lot of us are interested in here, especially small scale waves have to be parameterized using resolved or grid scale variables in operational weather and climate GCMs. These parameterization schemes often rely on linear theory, which assumes that the waves are small amplitude and monochromatic. So one of the shortcomings is that they can't account for any weakly or fully nonlinear effects. And so the hope is that we can, by better constraining these parameters, or the hope is that by better understanding nonlinear IGW evolution, that we can better constrain these parameterization schemes. So that brings me to the question that I addressed in a recent project, which I've submitted recently. And that is, we wanted to know, how does the nonlinear interaction between a 3D wave packet and its induced mean flow affect the wave packet transmission and reflection in a retrograde background flow? So I'll start with just a little bit of background. Small amplitude waves have a frequency which we denote by omega naught. And this frequency can be Doppler shifted by the background flow to give us the Doppler shifted frequency, which we call capital omega. And with this theory, we can predict the height at which waves are predicted to reflect just by equating the Doppler shifted frequency and the background buoyancy frequency. We can also predict the path that a wave packet is predicted to follow through the fluid with this set of ODEs, which are basically just transport equations. And we get the vertical wave number as a function of height just by rearranging this Doppler shifted frequency equation here. So to illustrate, this is the background flow profile we were interested in. It's effectively 0 below some onset height ZS, over which a distance LS, it transitions to this nice linearly decreasing retrograde profile. And I've also included just the expression for the shear itself, and I've indicated explicitly here that this is a retrograde flow. So if we go to, if we were to predict the path of this wave packet, I've indicated by the parallel lines here just what the lines of constant phase would be. So as the wave packet propagates up into the background flow, it gets its frequency gets Doppler shifted so that the wave phase eventually becomes vertically aligned. At this point, the wave packet has no vertical velocity, or no vertical group speed, I should say, but it continues getting Doppler shifted so that it eventually reverses its orientation and starts propagating back down and out of the shear. So all this was for small amplitude waves. It turns out if we have a moderately large amplitude wave packet, then these wave packets can induce a flow that locally accelerates the fluid in the vicinity of the wave packet. For the 3D wave packets we're interested in, the induced flow is what we call the Bretherton flow, and its horizontal components are given by this lovely Fourier integral. And crucially, I'll just note that the modulus squared of the amplitude with this hat is the 3D Fourier transform of the square of this assumed Gaussian envelope function here. To actually illustrate the induced flow, I'll just have a sample streamwise velocity profile here. So red is velocity crests, blue is velocity troughs. And if we filter out the wave packet and blow up the color scale, you can see this nice Gaussian structure to the induced mean flow. And I've indicated here by a solid and dashed lines 1 and 2 standard deviations about the center of the wave packet. If I take in the right panel a horizontal slice through the induced mean flow, you can see that it's positive through the center of the wave packet and negative along its spanwise flanks. So it really has this horizontal dipole-like structure. And it turns out that the wave-induced mean flow can act to allow the packet to penetrate partially above the reflection level. And the condition for that penetration is that somewhere the magnitude of the wave-induced shear has to be greater than the background shear. We know that at a given height, the strongest induced flow is aligned vertically with the center of the wave packet. So we can maximize this gradient here. And we can find that the strongest wave-induced shear is just below the center of the wave packet. If we substitute that back into the penetration condition and do a little bit of arithmetic, we can get this reflection level penetration condition, or this prediction here. And I've plotted this in the panel to the right, which basically says for a wave packet that propagates initially at some angle as measured from the vertical, basically as the shear strength increases, you need a larger amplitude in order to penetrate the reflection level. We wanted to get quantitative with this, of course. So we had to identify a conserved quantity that's conserved in the presence of a background flow. And we chose to work with the pseudomomentum. So for 3D wave packets, the pseudomomentum density is given by this expression here, where we've denoted by xi the vertical displacement and by zeta y the spanwise vorticity. And a u bar double prime is just 2 vertical derivatives of the background flow. And now to actually quantify the transmission above the reflection level, we used the Hilbert transform to pull out the upward propagating component of these waves, so we could construct the upward propagating pseudomomentum. We then integrated this horizontally and vertically above the reflection level and normalized by the initial pseudomomentum, which again is conserved. So it's the total pseudomomentum is the initial pseudomomentum. All right, so I have a few simulations to show. The first one, we have this shear strength of 0.002. We have a relative vertical wave number corresponding to waves that propagate upward at approximately a 22-degree angle. And crucially, this is a small amplitude wave packet where its initial amplitude is significantly smaller than the reflection level penetration predicted amplitude. On the right-hand side, I've got some profiles of the horizontally integrated pseudomomentum density. In black is the total profile, and then it's separated into this red upward going profile and the blue downward going profile. So I'll play the video once to show you the qualitative evolution, and then we'll play it a second time and look at the pseudomomentum curves. So initially, this wave packet propagates upward at about that 22-degree angle, as we would expect from linear theory. As it starts to propagate into the region where there's a retrograde shear, we can see that the Doppler shifting is causing these lines of constant phase to become more vertically aligned. And as the wave packet continues to propagate in that retrograde shear, we can see that the reflection is starting to occur. And as time continues, the wave packet continues to evolve, we see that it's still remaining as a single unit, and it appears that the whole thing is propagating back down, kind of following that loop that we illustrated with the ray theory equations. So if I play this again to look at pseudomomentum, you'll see that the upward going profile exactly overlaps the total profile initially. And then as the wave packet starts to propagate up into the background shear, the upward going pseudomomentum starts to give way to downward propagating pseudomomentum. And you can see that really developing now, especially below the reflection level. And we kind of have this, this continuous exchange from upward to downward propagating pseudomomentum. And then at late times, as the wave packet is reflecting, you can see that indeed the downward propagating pseudomomentum exactly overlies the total pseudomomentum. Right, so that was a small amplitude simulation. I now have an identical simulation that is now of moderately large amplitude, and it's approximately the same amplitude as the predicted reflection level penetration amplitude. And here what you'll see is not only reflection, but also partial transmission and some secondary waves. So I started this one, you'll see that because it's moderately large amplitude, there's this additional Doppler shifting by the wave-induced mean flow near the center of the wave packet. And as the wave packet starts to propagate up into the region with the retrograde shear, we have what appears to be some penetration, a little bit of reflection, and you'll see momentarily when it starts to evolve a little bit more, there's these secondary waves that are generated, which are also propagating upward. And you'll see, of course, at late times that these three distinguished features are apparent. We've got this reflected wave packet, we have the penetrating wave packet, and these secondary waves. So if I play this again to look at the pseudo-momentum curves, you'll see that the profile is actually growing in amplitude and it's narrowing, and this is due to modulational instability. Then as the wave packet starts to interact with the background flow, of course, we have the upward propagating pseudo-momentum giving way to downward propagating pseudo-momentum. And as the wave packet continues to evolve non-linearly, we can see that there's kind of these two peaks. There's the downward propagating peak, which is starting to translate below the reflection level, but there's also this distinguished set of upward propagating pseudo-momentum peaks that appears to be more or less fixed in time, at least in an integrated sense, and that's the penetrated wave packet. So we did a number of simulations. One of the things we wanted to look at was because the transmission above the reflection level is a transient quantity, we wanted to quantify the maximum that we could find in our simulations. And that's what I've shown in the first panel here in the black data points. So we looked at waves that were strongly non-hydrostatic and slightly more hydrostatic here. And in general, we found that the maximum transmission in time tended to decrease with amplitude. The exception, of course, being for these most strongly non-hydrostatic waves, which really didn't exhibit a maximum at all. They just continued to penetrate. So to try to capture that, we looked at the upward propagating pseudo-momentum integrated above the reflection level at this fixed time of 400. And we can see that as amplitude increases, there's just this continuous penetration above. We also looked at the time of peak transmission, and in general, we find that as we increase amplitude, it takes longer for that peak to be achieved. And then we were interested to see in how long it takes for that peak to decay to half of its peak value. And we see that as we increased the amplitude of the wave packets, the upward propagating pseudo-momentum that penetrated above the reflection level tended to linger for longer. So to summarize, we know that small amplitude waves have their frequency Doppler shifted by the background flow, and this ultimately leads to the reflection of small amplitude waves. If the waves are of moderately large amplitude, they induce this vertically jet-like and horizontally dipole-like mean flow, and this flow can permit the wave packet to transmit partially above the reflection level. We also know that moderately large amplitude wave packets can not only partially transmit and reflect, but also generate secondary waves. In terms of future and current and future work, I mentioned that we've submitted this manuscript and it's currently under review with physical review fluids. And ongoing work is to introduce the anelastic effects into the theory and the numerics. So with that, I want to thank you all for your attention, and I'm happy to take any questions.
Yeah, thank you very much. Are there any questions for Alain? And again, I'd invite you to please put them into chat if you have any, or just let me know that you'd like to ask one.
I have a question, Adam.
Yes.
Not following the rules, but go ahead.
Well, I let you know. So yeah, sorry, I don't have the chat open yet. Actually, I do. It's just off screen. Alain, I was just wondering, once you get into that high shear region, right, for your large amplitude cases, is there any change to the modulational instability, or is it just basically you run out of room for the domain you're numerically integrating it on?
Well, we have some simulations we looked at where because the wave packet is I should say, if we think of the lines of constant phase as being representative of whether it's more or less hydrostatic, we know that as the waves propagate into that shear region and they become more vertically oriented, we expect them to become more modulationally unstable. But this isn't like an immediate effect. So we see that there's some complicated dynamics where some parts of the wave packet seem to be acting under like a more modulationally unstable regime, and then as it reflects, it becomes more modulationally stable. So that's what we see qualitatively. In terms of the domain height, the pictures have shown, including this snapshot here, this is not the full domain. So really, we cropped these images to look just at the region of interest.
Thanks. Are there other questions? Okay, from Francis, do you want to ask your question?
I'm happy to. So thanks for the talk. I was just wondering about how in decomputing you were doing, how well resolved the waves were.
That's an excellent question. We're working in a triply periodic Fourier domain, and the way we discretize the waves is by setting a minimum of 16 grid points per wavelength. And that's in the horizontal. In the vertical, we wanted better resolution, so we set it to 32 grid points per wavelength. So that I think hopefully gives a sense of what the resolution is like relative to the waves themselves.
And are these high order schemes you're using to resolve them? To resolve the solution?
Sorry, are you talking about the spatial scheme or in time?
The spatial scheme.
Yeah. It's a Fourier method, so I think we can look at the spectrum of the waves, and we see that just about everything of interest is concentrated far from the highest spatial wave numbers. So we think they're fairly well resolved. And the nice thing, of course, with a Fourier method is it's more global versus like a local method like finite differences. So we're reasonably confident that these are good discretizations. If we had the computer power, we would obviously go higher, especially in the vertical, because 32 is good, but it could be better. But we still think that we capture all the qualitative effects, and we get a sense of what it does quantitatively as well.
Thanks for the answer, and I would say that 32 is pretty great, actually. So thanks for that.
All right.
Oh, well, I'm glad to hear it. Thank you.
Thank you very much, and thanks again. Alain, I think in the interest of time, we need to move on to our next speaker, Nicolas Castor-Volker.
All right. Thank you for the talk, Alan, and thank you for the introduction, Adam. I'll share my screen here. All right. So, hi, everyone. Today, I'm going to discuss the sensitivity of internal solitary waves to localized patches of mixing. This is some work that I and my supervisor, Mark Stasna, have done at the University of Waterloo in the Applied Math Department. So the main equation we're solving is the Dji equation. And this is how we simulate our waves. And the way I like to think about it is a machine. So this little Dji machine, you feed it a stratification, you feed it an available potential energy, and it spits out this little coordinate here that tells you how the stratification is deflected, and it also tells you the wave speed. This little coordinate, this eta here, can also be used to describe the velocity profiles that are induced by this wave profile at this potential energy. So here I have the streamwise velocity profile, and you can also get the vertical velocity profile. Our project is taking this stratification here, which is if you take a vertical slice, it's this little tangent stratification. We hit it with a mixed layer that's much weaker than the baseline stratification. And then we get this perturbed stratification and feed that into the Dji machine and see how it changes the wave. So with the preliminaries out of the way, let's talk about why you should care. Well, as we all know, the ocean or a lake, we kind of a warmer mixed layer on top and a sort of homogeneous cold layer on the bottom. And if you just kind of go like this with your thumb and make a first approximation, you can kind of just think about it like this little two-layer thing we have right here. And in this little boundary between the warm and the cold, we get a waveguide in which the waves can travel. Now, this upper layer, it could be perturbed by a number of things. You could get a storm, perhaps you're getting runoff, maybe you're getting a hyperactive porpoise swimming through the area. Whatever happens, you can get sort of mixing or localized patches of mixing, overturning in some part of the stratification. And Mark and I are just asking ourselves, well, hey, how will that affect the wave? Now, some of this is based off of previous or inspired by previous work of my supervisor, Mark, and his supervisor, my grant supervisor, Kevin Lamb. And what they did is they looked at a linear stratification and perturbed it. Now, the thing about linear stratification is that when you put it into the DJL machine, you don't get a wave out. But when you hit it with a little nonlinear perturbation, then you get a little nonlinear wave coming out of it, a little DJL wave here. And what they found is that if you have the perturbation at a certain depth, you get a wave of elevation. And if you make that perturbation a little shallower, then you get a wave of depression. They did get many other results too, but I found this is the most straightforward and easy to understand from their work. So our work, building on that, uses a nonlinear profile. So here I have the original wave that's fed in, that is created by that stratification being fed into the original stratification being fed into the DJL machine. Then here I have the perturbed wave at the same available potential energy with the little perturbation. And then here I have the difference between the two. So the naked eye doesn't see too much difference between these two figures, but as you can see, there is some appreciable difference. And it is about 1 order of magnitude greater than the difference of the perturbation. Likewise, you get differences in the velocity profiles. And I'm going to note that what we'll be comparing or evaluating in the experiment is the middle, or we'll be comparing the middle profiles of the horizontal velocity of the waves. So as I said, we're going to take a little layer, we're going to have a perturbation, we're going to vary it along these depths. And we're going to ask ourselves, how do the velocity profile, or how does the velocity profile at the center of the horizontal velocity change with the depth of the perturbation? Well, we found that there was a sort of peak change when you have the perturbation at this height, and then we fixed the perturbation height there, and then we varied the width and the amplitude of the perturbation, and then look to see what happens. And just as a reminder, this is the perturbation and the resultant stratification. All right. So before I go into the experiments, I should tell you that we didn't just compare waves at a common APE, as I described earlier. We wanted to describe we wanted to look at the center velocity profile, and also we also looked at the wave speed, although we don't talk about it here. We want to compare these sort of variables that feel odd to compare at waves of different heights. If I have waves at different heights, obviously they're going to be at different speeds. So Mark and I, we figured out a way to, after you calculate all your waves, and pick out waves of a common height, and then we compare their velocity profiles and their C's. So we basically compute the original waves, compute the perturbed waves, figured a way to compare the perturbed wave and original wave of a common height, and see how that changes their center horizontal velocity profile. All right, so now let's go over the results of the experiments. So on the y-axis, I have the L2 difference of the middle velocity profiles between the perturbed and unperturbed wave. And then down here, we have the amplitude of the wave, or the height of the maximum height of that eta coordinate. What we see, very interestingly, is that larger waves end up being perturbed more than smaller waves. We also see that as you decrease the height, we get greater perturbations, especially for waves beyond about 20 centimeters. However, that boost we get from the perturbations, so here we now have the perturbation depth axis added, we see that that effect dies off as the perturbation gets deeper and deeper. Next, we varied the width at that height where we saw the maximum change in the L2 error. And we found that as we increased the width, we also saw a greater change in perturbation. And as last time, we saw that larger waves are perturbed more than smaller waves. Although this doesn't increase monotonically. In fact, it kind of dies off after at the sort of like third largest wave. And once again, you see there's a critical width with the greatest impact, and then the effect starts to die off. Finally, we vary the amplitude of the wave. So here we have the L2 difference scaled by the amplitude of the perturbation. And we found that there wasn't much of a difference. So especially at the smaller waves, there's no difference. At the larger waves, we see some variation, but that could probably be ascribed to rounding errors or machine error. And we didn't find that varying the amplitude caused much of an effect, surprisingly. Well, beyond what can be explained by just increasing the amplitude of the stratification. So those are the results. In summary, we found that the horizontal velocity or vertical profile of the horizontal velocity at the center of the tank is most sensitive to shallow perturbations. We found that generally larger waves are more sensitive to perturbations than smaller waves, which is to me the most surprising result. And then we found that the L2 error of the difference between the velocity profiles isn't changed too much by changing the perturbation amplitude. That is, it has no appreciable effect. So this work is extremely preliminary right now. We are working on figuring out how we want to type it up and where we might want to submit it. So there are so many directions, and I've just listed a few here. First of all, you could change the order of the experiments, right? So maybe you could go at an arbitrary depth, find a width that creates the most critical, the biggest change, and then vary the amplitude and height with the profile of that width. Maybe you change the shape of the perturbation entirely. We had that little odd curve. Maybe you could hit it with some white noise. Or maybe you can use an entirely different stratification, such as a quasi 3-layer or a more a realistic surface stratification. Well, that's it for me. I appreciate you all listening, and I open the floor to questions.
And thank you very much, Nico. And we have our first question from Susan. Did you want to ask it yourself, Susan?
Sure, if it works that you can hear me. So
Yes,
thank
go
you
ahead.
for a nice talk.
Thank you.
I thought I saw that your density plots after you added your little perturbation were actually unstable. Is that intentional? Does it matter? Why are you running with unstable?
So I'll go to the stratification pictures. So yeah, it is a little unstable. Okay, I'm getting lost here. It is a little unstable, and that did make us kind of take a pause, because maybe our DGL solver would blow up and get angry at us. But it's such like a slight unstable overhang that it's not a big deal. Now, as to whether or not it's intentional, it is intentional. So this is the profile that my supervisor and Mark and Kevin used in their studies, and it's just kind of like a first approximation to a mixed layer. We just make it odd across the the density axis, and when you integrate it, it averages out to like no real perturbation if you do the vertical average. The instability is just kind of like a necessary evil, I guess.
Okay, thanks.
No problem. Thank you for the question.
All right, and we have another question from Chris.
Hi, as I said in the chat, do you have any linear theory backing this up? It looks like, in a sense, you're kind of looking at a type of adjoint equation where you're taking the wave as output and you're seeing how that varies with respect to variations of the stratification. So that's kind of looking at variations of the parameters of the DGL equation, where the parameter here is the stratification. So that feels like it should be approachable with a perturbation type of analysis, maybe giving you an idea of what to expect, especially because your next to last graph showed relatively little nonlinear impact. Sorry, the varying the amplitude of the perturbation. I think that one. It shows relatively little amplitude variation, at least at that kind of scale. But 10 to the minus 4 squared is also pretty tiny. So you might have some benefit to that kind of perturbation analysis. Sorry, question being, have you thought about this yet?
No, we haven't done any sort of linearization or asymptotic or linearization yet. That's a good suggestion. I really appreciate it, and probably scribble around and play with that later this week.
Okay, enjoy.
Thank you, Chris.
Are there other questions for Nico? Well, I have a quick one. You know, for someone who doesn't work on this problem on a regular basis, I was intrigued to hear you say that you were surprised that the larger waves had a higher sensitivity to the perturbation. So could you describe why you found that a surprising result?
Well, it's really naive on my part. It's just I always assume that, you know, if you have something tiny and you hit it, it's going to be bothered more than something big. I just figured, you know, just assuming that bigness would mean more robust. Maybe that's because, you know, I'm still a young student, and maybe some of the more senior in the audience would not expect that. But I guess just kind of intuitively thinking that bigger means more robust is why I got surprised.
All right, thanks. So we have time for one very quick last question. And if we don't have any, let's thank Nico again and continue on with University of Waterloo and Mark Stasna presenting a data-centric look at internal waves in late winter lakes.
Thanks, Adam. Okay, here it is. Ooh, let me shrink everybody down so I can actually see my. Oh wait, I have to shrink you all first before I go full screen. Why is it not letting me do it? Okay, here we go. Now you're all tiny, and now I can go full screen. Perils of Zoom. Okay, so I'm going to tell you kind of about a strange problem in internal waves. I was kind of excited about it, and the look back at it is, I mean, I've been doing internal waves a long time. You know, I started out doing sort of the variational formulation for the equation Nico talked about, right? The Dubray-Jacotin-Long equation that governs large amplitude internal solitary waves, and then I started asking questions about, well, what other kinds of waves are there out there, and nonlinear waves in particular. And this is a case where some came up almost completely by accident. So I'd like to thank my entire group, obviously, but Andrew Grace, my senior PhD student, for a lot of really helpful discussions. Okay, so internal waves in general, right? So on the right, there's a very famous picture from Farmer and Army in Night Inlet, right? So in Night Inlet, tidal flows drive ocean currents across a glacial sill, and they generate a variety of waves. Some of them are gigantic, like the monster around the number 200. And some of them are relatively tame, but still fairly large, like the ones inside the yellow ellipse. And those would be sort of internal solitary or solitary-like wave trains, to be more precise. And they do all sorts of things, right? They can stir up nutrients and provide good places to feed for fish. They can break stuff when people are trying to drill under the ocean. And they can modulate surface waves, like you see in the upper part of the picture, where you have the research vessel passing these bands that are actually even visible from space. So this has all been covered over many years by many different people, but I just thought I'd kind of throw it out there. But because they're horizontally propagating waves, all they need is a stratification, right? So late winter in cold lakes does have a stratification, but it's got kind of an exotic one, right? So fresh water has a density maximum around 4 degrees centigrade, which means in late winter, you have an inverse stratification, right? So the 4-degree water is at the bottom and colder water is up above. So if your ice is fairly clean, right, the sun starts to get stronger, and so it starts to heat up that water, okay, and cause it to go statically unstable, example that Sue's mentioned, and sort of little by little mix. And so, of course, things aren't quite that tidy in nature, and but there's a host of sort of interesting problems, and some of those are covered by this kind of neat review that I grabbed this picture on the right from. So I generally find that limnologists kind of draw amazing conclusions from single point measurements. So there's a well-known study site up in Alaska, Toolik Lake, that Sally McIntyre and her many different students and postdocs have been studying it for a long time. And there are a variety of puzzling things out of those measurements, kind of just rummaged around in my mind for a long time. So this is a picture of the two lakes they measured in, okay? And the lakes are sort of 10-ish meters deep, right? And they found mixing processes and waves in late winter. And in particular, this is a fairly busy figure, but what they found was that because the temperature differences make for density differences that are small, you also have to think about suspended matter, right? Or basically the chemistry as well, okay? And when you put it all together, what you end up getting are stratifications that are a little more exotic than the typical sort of single pycnocline ones that Nico just showed you and that are commonly reported in the literature. So if you look at panel B, right, you'll see an example of a near surface pycnocline and then another one near the bottom. So I thought, oh, this would be fun. Why don't I look at some very basic wave generation like you might do in an experimental tank, right? So stratified adjustment for stratifications like this. So I simulated mode 1 waves. They were fairly tidy. I could get theoretical descriptions of them, no problem. And I said, okay, let me try mode 2 waves because Alicia Cortez in her paper reported some mode 2 wave activity. Okay, so mode 2 waves are the second mode. They're typically smaller in the ocean. They have less energy and they have some, they can't quite be solitary, but they have some interesting sort of math and physics behind them. So I just thought, okay, well, let's take the stratification. So in the upper left, you see the stratification. In the upper right, you see the profile, and you perturb it a little bit, okay? And I'm really focusing on the far left of the domain in this picture. And in the bottom, I show you 5 hours later, a couple hundred meters down the tank. So these waves are really slow, okay? And you see this very long mode 1 small amplitude solitary wave indicated by the red arrow, and then a mode 2 wave indicated by the green arrow. And the mode 2 wave looks kind of weird. Near the bottom, it looks like a concave mode 2 wave, like some people have talked about in the literature, but in the upper pycnocline, it doesn't look like that at all. It doesn't look tidy at all. And in fact, when you do a Hofmüller plot, right, so you look at the velocities near the top and the velocities near the bottom, right, the leading wave is kind of what you expect. It's got one polarity near the top, opposite polarity near the bottom, life's good. But if you look at the second wave, right, which is the sort of steel blue arrow, what you find is kind of this weird sort of bulging behavior. And if you look at that same area up near the top, right, which would be sort of these blue regions, you see that it's even more irregular, okay? So I looked at that and I thought, oh, that's weird. I should try to figure out what that is. So the first thing I did, I said, you know, I don't really want that mode 1 wave there. So I decided to just perturb the bottom pycnocline because that's the part that looked like it had a clean structure. So I did that, and that's shown in the upper left. Again, the profile, just for completeness, is again shown in the top right, or in the upper right. And then the results of the simulation at some time later is shown below. And again, right, I've got this rather tidy sort of wave structure near the bottom, but something that doesn't look all that clean at the top. So then instead of making something like this, I decided to get smart, right? I said, let me calculate about how fast this object moves, okay? And let me switch into what I consider to be as close as possible to a single propagation speed. Now, it turns out that it doesn't actually have an exactly constant propagation speed, but it's pretty close. So here's what you get when you do that, right? So near the bottom, you get something that kind of looks like a solitary wave. It looks like it's slowing down a little bit, right? And it looks like it sort of pulsates a little bit, right? It sort of wiggles a little bit, right? But near the top, you get something fundamentally different, right? You get something that actually looks like a wave packet, right? So waves start on the left, they kind of get bigger, they get more red in the middle, and then they fade out as they leave the front of the envelope. So a lot like what Alain showed for his vertically propagating waves in the first talk of the session, okay? So this amazed me, right? Because this is a mode 2 wave, right? With very different structure near the top and bottom, okay? So it can't be described by sort of the standard sort of, I guess, perturbative type theories that we have, right? Because the vertical structure is just fundamentally different. So then the question was, how do you describe it, okay? So I started digging in the literature, and just for some context, here's an exotic kind of nonlinear wave. It's called a breather, right? So it's been out there in the model equation literature for 20, 30 years, right? Especially in Russian literature. And then Kevin Lamb in 2007 did some simulations of waves like this, right? They're kind of like nonlinear wave packets, but not quite. And so you see the Hubmiller plot up at the top right, and then some sample density plots at the bottom. And what you see is that this thing kind of just oscillates around, right? It seems to shed waves out the front. So it's not exactly solitary, but more or less solitary. So that's cool. That's a lot like what you're seeing in the picture on the right here. But the one difference is, right, and this really I was super excited about, is here both the pycnoclines, right? So it's a two pycnocline situation, just like mine, but they're fairly close together, and they both behave the same. Whereas in my case, they behave differently. So this really bothered me. Took a few weeks off and went back to my administrative duties, and then I couldn't leave it alone. So I thought, okay, well, if I can't come up with a sort of a paper and pencil theory, maybe I can use some data-centric methods for this. Okay, so here's the question. So since the near top and near bottom regions appear to exhibit different qualitative behavior, can we describe the wave in a compact manner using only data? And so we have a technique we developed by one of my former PhD students, Justin Shaw, which takes a standard method, right, the method of empirical orthogonal functions, or EOFs, and sort of this has been known a long time, right, since the early 1900s, as it turns out. And EOFs are great; they capture spatial patterns of variability. But there's been lots of papers that pointed out that EOFs themselves do not have a physical meaning. So Justin came up with a really elegant solution to get some physical meaning back by using cumulative sums of EOFs, right, to get back the physical solution. So what you do is you reconstruct the solution using one EOF, then you reconstruct it using two EOFs, then you do it with 3 and 4 and 5, and then you calculate the difference between that kind of solution and the actual solution. Okay, so it's like comparing a projection of something to the full vector, if you will. And then you plot that, and he calls that the error map. So that's the picture on the bottom right. And basically where you have these sort of peaks of red, right, that's where he calls it an interesting event. So for this example from his PLS1 paper, this is a solitary wave that runs out of stratification, so it kind of explodes, right? So the little green lines show you the different plots above. And basically the idea is you get peaks of activity after it runs out of stratification and becomes more dynamically active. So I said, okay, well, let's use this, right? And let's see how much I can get away with, okay? So in the picture on the upper right, okay, you've got the sample wave, wave-induced U at 19.33 hours, okay? And then below you have the 2 EOF reconstruction. And I mean, I got it wrong a few times, but even after I produced this picture, I was pretty sure this had to be wrong, right? But if you start looking at it carefully, you realize, no, it's not wrong. There are differences, but clearly the data set collapses almost completely with just the simple 2 EOF reconstruction, right? So you don't have a clear modal theory in this case, right? But you do have a 2 EOF reconstruction that basically reproduces your whole data set. So there's got to be some way to describe this object. And so I will point out, I mean, a long time ago, I read all these nonlinear waves papers. So there is a paper by Weidman about linear waves and nonlinear wave interactions in a bounded 3-layer fluid system, which suggests how you might construct a theory. But it's not an easy theory to apply, and I think that would be something that would be worth following up. Okay, and then in a shameless plug, I know Bruce Sutherland wrote a really great book about all sorts of internal waves, but this nonlinear wave stuff's never really had a proper outlet. So in the next couple of months, Springer will finally put out something I've worked on for a long time. So if you're interested, maybe you can look for it. But I'll go back and leave it here. Thank you very much.
Thanks, Mark. So are there any questions for Mark? Francis.
Okay, thanks, Adam, and thanks, Mark, for a great talk.
Oh boy. Well, while Francis is frozen, I'll invite another question rather. We have a couple minutes for questions. Chris?
Unmute, that helps. How does okay, looking at the paired stratifications here, the mode 2 wave is predominantly a wave of elevation at the bottom and stuff at the top. How does the phase speed of that mode 2 wave compare to what you would have if you had only the bottom stratification and you had just a wave of elevation there? Is this a wave primarily described by the bottom pictic line that just has stuff happening at the top, or is the stuff happening at the top having an impact on the speed of this combined mode?
Well, I mean, I'm not sure if the speed's the right way to look at it, right? I mean, the speed differences are going to be tiny almost no matter what. I mean, I guess I would say that they are phase locked, right? Which is kind of amazing.
Well, that's what gives rise to the question. If there's phase locked in that the top is doing something dynamically to affect the entire wave, but then there's also phase locked, like the top is just diagnostic in the same way that we can observe internal solitary waves by looking at the extremely tiny ocean surface signatures, even though we can pretend that the ocean has a rigid lid while we're computing this.
Yeah. Okay. I mean, I guess the basic answer should be someone should head up to Alaska to try to measure a little bit more than just a single point in those lakes. If there actually are propagating waves. I mean, yeah, I mean, I should do what you suggested, but my intuition is that, yeah, I'll get something that looks fairly close, but I will get nothing like what you observed near the top, right? And so the analogy that I have in my head is that, you know, it's fairly well known that mode 2 waves have these little tails, right? So there's that classical paper by Achilles and Grimshaw with all this really fancy perturbation theory. So this is like that, except instead of the wave being behind, it's literally right there. Right, it's right above, and it's kind of dancing over top of the mode 2 wave underneath the wave of elevation. Is Francis back, or is he?
Francis is back, and if you can ask your question quickly, well,
I will ask it later because it's a longer question, but thanks anyhow.
Okay, sorry. And actually, well then, Paul, did you want to ask about what the UFs look like? Well, I'll ask Paul's question. Do you actually have a
All right, yeah, no. What do the two EOFs look like, Mark? I was just asking.
What do the two EOFs look like? I don't have them on me. You know what? When I come to Toronto in a couple of weeks, I will have a picture of the two EOFs.
But is there one? Are they? Is one barotropic, the other baroclinic, or are they sort of bottom?
So these are baroclinic waves. So both will be baroclinic. Yeah, I mean. I'll look again, but I didn't think either of them was particularly helpful. It was really the reconstruction that was helpful, and I did. Maybe I'll put in some of the details of how I did it. I did a lot of different reconstructions.
Sure. Yeah. Very nice. Thanks.
All right. Well, thank you all very much. And I think, again, in the interest of time, we can move on to a poster presentation or a brief overview of a poster in our session from Yasaman Afshadapur. So please, I invite you to present your poster.
Thank you. I will share my screen. Can you see my screen?
Yes.
Okay. So my name is Yasaman. I'm a master's student at the University of Calgary, and this work is a cooperation between me, Dr. Shu from Bedford Institute of Oceanography, Dr. Myers from the University of Alberta, and my supervisor, Dr. Joe. And our work is titled Numerical Investigation of Thiopigno Mixing in the Kidagmiat Sea. This sea is located in the southern Canadian Arctic archipelago. It is a semi-enclosed basin, an east-west waterway, and it has particular features. So it receives massive freshwater input from rivers. It is surrounded by shallow sills to limit seawater exchange, and it has a significant ice-free period each year. All of these features result in this region being different than the northern sections of the archipelago. And again, the freshwater input from rivers and ice melting have resulted in this region having a stronger stratification. This stratification is strong, so diapignal mixing becomes particularly important because increased mixing results in increased nutrient fluxes and higher biological productivity. So we decided to study mixing in this region. We have used data from a numerical simulation based on NEMO version 3.4. The model is configured for Arctic and Northern Hemisphere Atlantic. It is called ANA12. It has a 112-degree resolution and 50 vertical levels. This model is configured and run by Dr. Meyer's group at the University of Alberta. And we have used a volume averaged advection diffusion equation to quantify mixing in terms of a mean effective diapycnal diffusivity for each isopycnal surface. And I've just put a few examples of the results that I've put in the poster. So we have calculated monthly mean diffusivities at different regions within the Kidagmiat Sea. And we have detected seasonal patterns. And in order to discover what is causing those seasonal patterns, we have looked into a few energy sources and tried to make a few estimates of the contributions that each energy source is putting into the mixing process. And you can see the center, like lower part here, there is a time series of the contributions from different energy sources. Negative means a steering contribution, and positive means a stratifying effect under stratification. And that's it. I hope you look at my poster, and I'm open to any questions. I would be happy to answer them.
Thank you very much, Yesaman. We have time.
I tried to make it short. You told me 3 minutes. I can go on, but I tried to keep it short.
No, that's very much appreciated. We have time for one quick question. Susan.
Interesting set of sources of mixing. Why not tides?
That's because our model, the configuration of ANA12, does not have tides in its initial conditions. So that particular configuration does not include the effect of tides. So because of that, I have not calculated the effect of tides in this, but our next model is going to include tides.
Thank you. Thank you.
Thank you.
All right, and thank you very much. And I encourage everyone to attend Yesaman's poster presentation and engage with her some more at that time. So I'm going to suggest now we move on to our next talk. We actually started this session 5 minutes late because I don't know how to read a schedule. And so this will get us right back on time, starting with Peter Taylor, who's going to speak to us about constant flux layers with gravitational settling, deposition velocity implications.
Okay, thanks very much. Let me try and share my screen here. Go to the PowerPoint version, although having seen someone crash their PowerPoint presentation earlier today, I began to wonder if I should just use PDF. Anyway, oh no, I've moved forward one. Okay, so constant flux layers with gravitational settling. This all started off, and the rather gray background on this slide illustrates this. It started off when we were working on modeling fog and modeling marine fog. And when we were running WRF and the WRF model and other models of the fog evolution, generally they tended to be too thick. And one of the reasons that occurred to me was that, you know, the water vapor condenses in the air, produces these droplets. They may settle somewhat towards the surface, but also when they get near to the surface, there's going to be turbulent mixing down to the surface, which I envisage would be a sink for water droplets. So we spent some time working on this, and things improved somewhat in the modeling. And I guess one of the posters associated with the second half of this this session is with Jackie Chen's more recent work on modeling with WRF. So as a sort of spin-off from that, I thought it was worthwhile pointing out that other material, as well as fog droplets, can deposit to water surfaces. And at the moment, there's a lot of interest, at least around York, on microplastics. These little fragments of these microplastic aerosols generated perhaps by the effluent from your clothes dryer or from cars driving along roads and breaking up their tires. And these then drift out over the lakes or the ocean and deposit to the surface. So you'd have a situation where you've got a source up above the near surface turbulent boundary layer, which then is depositing to the surface. And if you know anything about turbulent boundary layers, you'll know that one of the standard concepts is a constant flux layer, in which the downward flux of momentum, or the downward or upward flux of heat or water vapor, or in this case aerosol, can be independent of height. And if you make those assumptions and do some dimensional analysis, then there's the classic Monod-Nabokov similarity theory, which tells you what the nature of those profiles might be. And in the simplest case, which is what I'll start with neutral stratification, no stable layers, nothing unstable, then you end up with logarithmic velocity profiles, logarithmic temperature perturbation profiles, and so forth. And one can think of that in terms of an eddy diffusivity, where the velocity scale is given by the friction velocity, square root the shear stress divided by air density, and a length scale, which is essentially dependent upon the height above the surface. You're getting larger eddies as you get further from the surface. So turbulent diffusion to the surface is sort of fairly well understood. And the other issue that comes in is this gravitational settling. So suppose you have a constant flux layer in which you have both gravitational settling and the turbulent flux. So you can envisage looking at these two quantities. Terminal fall speed, which we'll call Vg. So you just got the mass, or the mass minus the buoyancy force. So gravity minus the buoyancy force acting on this aerosol particle, and it's slowly falling down with velocity Vg, and there'll be a drag, which if the particle is small enough, will satisfy Stokes' law. So the drag coefficient is inversely proportional to velocity, essentially. And what that leads to is a drag which is proportional to velocity. And if that's true, then you end up with no additional turbulence impact on the mean gravitational settling velocity. So it's reasonable to say, okay, up here, well above the surface, perhaps, you've got a downward flux of essentially the mixing ratio of aerosol, QC, which is just the gravitational settling velocity times the concentration. So if we think in terms of that's what's happening fairly well above the surface, down here near the surface may be a sink of the aerosol. And the flux to the surface is largely going to be controlled by turbulence, and you'll end up with a deposition down here near a deposition velocity down here, which is dependent upon the friction velocity and the distance above the surface, essentially. So we've got these two downward velocities, the gravitational settling velocity and the deposition velocity. And if one goes into the literature on aerosols in terms of air quality models, you'll find that people manage to combine these two, but not in a very thorough or not in a very clear way, somewhat arbitrary ways. So that made me think about what happens if we combine gravitational settling and turbulent flux within the concept of a constant flux layer. So we'll say you've got this gravitational settling and you've got the turbulent flux, so an eddy diffusivity times the gradient of the concentration, and that's going to be a constant, saying there's this constant downward flux within this boundary layer, which is not evolving in time and is horizontally homogeneous, which, you know, one can argue is reasonably representative of some marine fog situations. So we're saying this is the eddy diffusivity, which is what I've put in here. And so now we've got an equation. The other thing to remark is that Z0C is a roughness length. And I'm assuming that roughness length can be specific to aerosol particles, although in some of the examples I'll use, it's the same as the roughness length for momentum. So roughness length for momentum, heat, and water vapor can all be different within this idealization of the constant flux layer. So take this equation, we can solve it. It's the linear equation in QC. And so you throw in an integrating factor, and you'll end up with an equation like this. And if you assume that the concentration of aerosol is 0 at the surface, then you get these solutions. And you can either express those in terms of the height above the water surface or the surface, or in terms of its logarithm. So you get a rather neater solution in terms of zeta. So these then are profiles of constant flux layer, profiles of the concentration of aerosol or fog droplets or whatever in terms of height above the ground in what I'm calling a constant flux layer with gravitational settling. And it's worth saying that in the limiters, well, first of all, I should highlight that I've defined this parameter S, which is the ratio of the gravitational settling velocity divided by kappa U star, where kappa is the von Karman constant, which always gets thrown in for historical reasons, but it's convenient to put it in here. And in this limit, as S tends to 0, it's not quite obvious what you're going to have. You're going to have 0 divided by 0. If you take the appropriate limits, then that gives you a standard log profile for the concentration. So what do these look like? What I've done here is to scale the concentration against the value at 50 meters, assuming we've got a 50-meter deep constant flux layer. And if you've got this simple log profile, you get this blue curve, S equals 0. And as the gravitational settling velocity increases, and these are sort of the reasonable values you might expect to get for small aerosol particles, then that produces this curvature in these profiles. And in the limit, if you like, as S approaches infinity, you'd have a constant QC right down to the surface where it would drop to 0. And we can plot that on a linear scale or on a log scale where you've got this straight line. And just comment that these are calculations made with a roughness length of 10 centimeters. And yeah, and everything is normalized by the concentration at 50 meters. We can ask, what is the relationship between turbulent transfer and gravitational settling? And again, if we look at that, we can say, all right, if you've got fairly small values of S, then although gravitational settling is important, as you get down to the surface, it starts to change. So you've got an increased amount of turbulent transfer. And even up here at 50 meters, there's still a sort of 30–40% component of that downward flux associated with the turbulent transfer rather than just with the gravitational settling. So as I said, one of the issues is, how do you relate this to deposition velocity, the sort of deposition velocities that air quality people use when they're trying to model the transport of air pollutants or aerosol components of air pollutants. And they use a deposition velocity. And there are various formulations, but the one produced by Zhang et al. From Environment Canada and Slin rather have used this formulation. And they use the gravitational velocity plus an additional component which they represent in terms of resistances. And there's a recent review by Farmer et al., which gives all sorts of values. One of the things that
2 minutes, Peter.
Okay, one of the things that puzzles me is that they very rarely talk about how this deposition velocity should vary with height. But if you take our constant flux gravitational settling model, then this is the formula you get, which is somewhat different from those. And one can see how these differ in these plots. So the red pluses are the air quality people's models, and this is the constant flux layer. 4 different values of S. So it's not a great difference, 20, 30%, but I think it's something worth considering. Just to go back, remark that this was all prompted by looking at fog, and next month there's going to be a big experiment out on Sable Island called Fatima, Fog and Turbulence Interactions in the Marine Atmosphere, led by Joe Fernando from Notre Dame. There's quite a bit of Canadian involvement. I had hoped to be able to make some measurements out there, but couldn't manage to get any funding for that. But other people will be, and it'll be interesting to see what measurements they make. And one of the things that Jakey will talk about in his poster is how different the measurements over Sable Island may be relative to the differences, maybe to the measurements that we would make over the ocean surrounding Sable Island. And we published a note in the bulletin on that. So thank you for your attention.
And thank you very much, Peter. And I think in the interest of time, we can take one very quick question if there are any. All right. Well, I think we should move on to our next speaker, Amir Atufi. Are you here, Amir?
Yes, I'm here.
Okay, grand.
Yeah.
And Amir is going to be speaking to us about turbulence dynamics and a stably stratified wall-bounded flow.
Yeah, thank you. Can you see my screen?
Yes. You want to make that full screen?
Yeah. Oh, hello, everyone. Thank you for attending this talk. So in this talk, I'd like to briefly introduce part of my PhD study working with Andrew Scott, Michael Wade, and Fazli Hossain on turbulence dynamics and energy cascade processes in stably stratified boundary layers. So the right figure basically shows a patch of locally erupted fluid within the surface layer of the strongly stable atmospheric boundary layer visualized by machine-generated fog, which shows the spatial intermittencies, which is one of the common features of a strongly stable boundary layers. Our understanding of such flows is still limited even up to today. So far more studies are needed to provide further insight into this problem. So here is the content that I plan to talk about this presentation. So I will first introduce the problem and why we should think about it. Then I'll briefly discuss formulation, dimensionless pyramidal, and the numerical method. Then I'll introduce the energy cascade processes that are involved in this problem, discussing the vertical scales. So the problem that I will be focusing on is essentially stably stratified open channel flow, which has many applications in atmospheric boundary layer, bottom oceanic boundary layer, and a river flow. So as I said, this is the problem that I'm addressing. It's the stable stratified open channel flow. This stratification is introduced by imposed cooling flux at the wall while making the top boundary either adiabatic or with fixed temperature. So in the latter situation, heat entrainment from the top boundary is allowed. So the governing equations are Navier-Stokes equation under Overback Boussinesq approximation. So with the choice of reference friction velocity, imposed temperature, flux, channel height, and fluid viscosity and conductivity, the non-dimensional parameter become friction Reynolds number, friction Richardson number, Prandtl number. Another important non-dimensional parameter that is often used in this problem is the ratio between the channel height and Molino-Wakov length scale, which can be shown is actually the ratio of the turbulence production in the logarithmic layer with respect to heat flux imposed at the wall. So this is an important quantity. So for the numerical method, we use Fourier spectral method in the horizontal direction and second order finite difference in the vertical direction while using combination of third order Ron-Zukov and Crank-Nicholson method. So the code we use is Hercules, which is the code that I've been working since my PhD and also developed by Pinky. So just to give an overview, some of the basic results. So by introducing stratification, the shear stresses at the wall increases. Basic decreases and basically flow accelerates. So you get increase in the bulk Reynolds number, while the friction Reynolds number decreases. So depending on the level of stratification, and the time scale that is related to the ratio of the Molino-Wakov length to friction velocity. So flow goes to the basically decay phase and then recovery and then coming back to the stationary state. So this is how flows look like. So if you have a strongly stable stratification regime, so flow becomes patchy where you have a region of active turbulence sit next to quiet regions. It turns out that at this time that the role of outer layer motions are actually quite important, meaning that if you filter them out from your dynamic, the recovery process will be suppressed and there will be complete collapse of turbulence. So because the nature of the flow at strongest stratification regime is patchy, so we've been thinking about finding a way to define turbulence quantities, which doesn't require necessarily defining a mean operation. So for instance, the definition of the turbulence production given here requires in the open channel flow geometry some sort of horizontal averaging. So if we use the concept of line vector divergence, which is shown here, that has two components. One is flexion product, the first term, and the second is entropy. So it shows quite promising feature in the sense that it will reproduce the peak of the turbulence production in the viscous region near the wall, and also it follows the temporal behavior while we are introducing surface cooling. Although it doesn't require definition of any mean operation, so you can have basically full velocity to compute this. Okay, so as the topic suggested, we're focusing on the turbulence dynamic, and the way that we're discussing it is through looking at energy cascade processes in the scale of wave number and vertical escapes. So in homogeneous turbulence, the Fourier spectral method is a great tool to address scale dependency in energy cascade processes. When we have inhomogeneity, as we do in stratified open channel, so the difficulty of having inhomogeneous wall normal direction can be treated by introducing a filter current that has dependence upon scale separation in vertical direction and some vertical scales. By doing so, we basically introduce two more dimensional parameter to our energy spectra. One is a scale separation in vertical direction, and the other is vertical scales. So it actually costs a lot of computational time to do this calculation. So one way to tackle this and prevent this computational complexity is basically discretizing vertical scales into different bands of viscous sublayer scales, buffer layer scale, logarithmic layer scale, and outer layer scale. So we only consider vertical scales of the size comparable to height of each of these layers, as shown in this plot. So if we do so, we see actually the most energetic vertical scales are those that are of the size of buffer layers, meaning that there is a strong correlation between near wall region and the size the size of the smallest vertical scales. We can look at the energy density spectra in horizontal and horizontal streamwise and spanwise scale, and we can basically identify at which vertical scale behavior of streamwise and spanwise scales are different. One interesting outcome of this analysis is for unstratified cases, the vertical scales of the size of logarithmic layer will connect the energetic region near the wall at the buffer layer to the outer layer. Such connections provided by the vertical scales of the size of logarithmic layer are suppressed as we increase the stratification, as shown between panel A and C. The other interesting outcome is, so this spectra shows self-similarity between spanwise scales as long as the stratification is not strong enough so that turbulence is still homogeneous in all horizontal direction. We can also do this analysis by looking at distribution of a streamwise scale at different height, as shown in these spectra. As we can see, the spectra of the logarithmic and buffer layer are quite similar, and also so the power law relation between vertical scale and horizontal scale can be seen in the viscous region. Another thing that we can look at is just by considering the buoyancy destruction in terms of variation in the spectral space and its dependency upon a wave number and vertical separation. So here we are showing the buoyancy destruction spectra average overall horizontal wave number. As we can see, so near the wall, so it doesn't show any peak. But if we compare the Osmondov scales, which are known to be the scales that are affected by presence of a stable stratification, the energetic vertical scales are affected only in the logarithmic region, meaning that our previous observation that near wall turbulence can recover after recovering within the stationary state is not so much dependent upon stratification. Basically, that's one way to explain this this observation. Just to conclude, so we show the dominant energetic vertical scales have the size comparable to the size of buffer layers. And we also showed that the energetic streamwise scales become larger with increasing vertical scales. Again, by looking at the energy density spectra, we show there is a link between vertical scales of the size of logarithmic layer that connects buffer layer to the outer layer, this link is suppressed as we increase stereo stratification. And also, we showed that the outer layer turbulence above Z plus, which is the height scaled by the viscous unit, above Z plus equal to 300 is a key requirement for recovery out of that intense suppression of the turbulence as a result of introducing a stereo stratification. Yeah, thank you.
All right, thank you very much. And we have time for a few questions. People would like to put those into chat. Okay, well, I can ask one. Amir, you in your analysis, you take a fixed surface heat flux, is that correct?
That is correct, yes.
Yeah. Have you considered the possibility of taking a heat flux which is actually flow dependent, as you might expect in an atmospheric situation?
Yeah, we've been thinking about it, but we haven't done it yet. But that would be very interesting, especially if you will have some time dependency into it. That would be very interesting. Yeah. Thanks.
I see Peter has a question.
Yeah, I was just going to ask, in a neutrally stratified boundary layer, one tends to think of longitudinal vortices aligned with the flow as being one of the features of turbulence.
Yep.
And I couldn't quite see whether these were suppressed in the stably stratified case, or whether you had anything to say about longitudinal vortices.
Yeah, so this is basically the Q criterion, the second invariant velocity gradient tensor. So that we use to visualize vortices in the near world region, and this is for the strongly stratified cases.
Yeah.
So basically, as you can see, so the effect of a stratification will suppress part of the horizontal plane, whereas at least for this stratification level, some part of the region can maintain those longitudinal or streamwise vortices, so they can, so that the self-sustaining process within those regions can maintain the generation of the streamwise vortices. Whereas in the other two quiet region, because of the strong effect of stratification, turbulence production is strongly suppressed. So you won't see those generational streamwise vortices.
Yeah. Okay, thanks.
All right. And thank you again, Amir. And I'd like now to move to the last speaker of the session, Donald Lai. You there, Donald?
Yes.
All right.
You should see my screen.
Absolutely. Donald's going to speak to us about kinetic energy spectra and the spectral budget of radiative convective equilibrium.
Hi, my name is Donald. I'm going to talk about my project on kinetic energy spectrum, spectral budget of radiative convective equilibrium. I should full screen it. All right. So let's talk about what is radiative convective equilibrium and talk about a bit on energy spectrum later. So radiative convective equilibrium is an idealized climate system driven by sensible and latent heat flux at the surface, and it is balanced by the radiative cooling in the atmosphere. And talk about energy spectrum using dimensional analysis. Komogorov suggested the -5 energy spectrum for 3-dimensional isotropic turbulence. And in atmospheric measurements shows that a -3 spectrum for the synoptic scale in the mid latitudes and a shallower -5 spectrum for the mesoscale. So while there is a general agreement on the explanation on the -3 spectrum, we don't know, there's no agreement on the mechanics responsible for the -5 power energy spectrum. So in this talk, we will talk about spectral energy budget and energy cascade in RC. And this is a picture of the -5 Hz spectrum in the tropics. And energy budget. So to understand the energy spectrum, it is useful to consider the energy spectral budget. So this is the budget. The rate of change of kinetic energy is equals to the sum of the horizontal nonlinear energy transfer, the divergence of vertical energy flux, the energy flux from the buoyancy term, the dissipation from the circuit turbulence mixing scheme, and the numerical dissipation. So this is how it looks like. I know people doesn't know like equations, and this is related to the numerical dissipation. So in order to compute the numerical dissipation, we need to know the modified equation, and this is how the modified equation looks like when we're using WRF. So this is how it looks like when we use WRF. And so as I mentioned, we use WRF to do our simulations, and the domain size of my simulation is 600 times 600 times 25 kilometers. Horizontal resolution is 4 kilometers. We ran it for 42 days, and we have periodic boundary conditions in the horizontal, and we have 199 vertical grids levels and in the vertical, and the vertical grid spacing is approximately 100 meters in the lower troposphere, the upper troposphere, and the lower stratosphere. So we use the TKE circuit turbulence scheme as our turbulence scheme, and there is no coriolis force, and the sea surface temperature is 302 Kelvin. We have 2 simulations in total. So when people talk about RCE, very often they would talk about something called self-aggregation, and that's why we have 2 simulations. One is aggregated, the other one is non-aggregated. So on the top, these are cloud water mixing ratios, and these the top three figures are the non-aggregated one. As we could see, when we say non-aggregated, we could see the convective core is randomly distributed. There's no significant aggregation we could see throughout time. But in the bottom 3 panel, we could see that as time goes, it got aggregate more and more until it comes aggregation, and it never actually disaggregate in a really significant way. Sometimes it disaggregate a little bit, but then it will come back and aggregates again. So these are the 2 simulations that we'll be looking at. So we'll be looking at these 2 simulations in terms of the energy spectrum, and this is the horizontal kinetic energy spectrum here, and we could see that in the non-aggregated simulation, the total energy spectrum doesn't resemble the -5 Hz spectrum, and the aggregated simulation, it actually resembles the -5 Hz spectrum a lot better. And we could see that here, the rotational kinetic energy and the divergent kinetic energy is actually similar in magnitude in both cases. So, and when we move on to the energy budget, we could see that the buoyancy term actually responsible for most of the energy gain, and most of the energy loss is actually from the vertical flux. So again, here is similar except at smaller scale. So at smaller scale, the vertical flux switches sign and become a gain in energy. And the other term is not that significant, except the dissipative term is very significant at small scale. So this green line is the numerical dissipation, and this purple line is the dissipation from the TKE circuit turbulence mixing scheme. So this is in the upper troposphere, And now we are looking at the lower stratosphere. So again, in the lower stratosphere, the non-aggregated simulation doesn't resembles the negative 5-Hz spectrum well, but it is a lot better when we look at the aggregated simulation. And also notice that in this time, the total kinetic energy is totally dominated by the divergent kinetic energy, which is different from what we see previously, where rotational kinetic energy is very similar to divergent kinetic energy. And also when we look at the budget, it also looks a lot different too. So when we look at the budget for the lower stratosphere, the vertical flux is responsible for the energy gain, and there are some energy loss from the buoyancy term, the transfer term, and the dissipation term as well. So I would like to point out one thing that notice that how the transfer term is significantly more important in the lower stratosphere. So when we look at the upper troposphere, it's actually quite weak. So it's not that significant, whereas the lower stratosphere is more significant. So also notice that this bump that we see here. So there is actually a significant energy gain in the mean flow in the lower stratosphere that we don't see in the upper troposphere. So we don't see that blue pump here. So which suggests that there are some energy actually flowing into the mean flow. So we could see the energy loss from the small scale and flow into the mean flow. Similar in the aggregate simulation, energy loss from the small scale and flow into the mean flow. So we have been wondering, so when we want to look at energy transfer, or we would say energy cascade, so we could look at the nonlinear transfer energy flux. So when we see positive, so this pi, when we see positive, it means that there is a forward energy transfer, and if it is negative, which suggests an inverse energy transfer. So these are the contour plot for the non-aggregate simulation and aggregate simulation. So as we could see, this is the upper troposphere from 6 to 10 kilometers. So we could see that most of this region, also in the aggregate simulation, most of this region are positive, which suggests a forward energy transfer or forward energy cascade. And in the lower stratosphere region, we could see that most of them are dominated by a negative like value, which suggests that there are inverse energy cascade happening here. So we've been wondering like why that happens, and we perform some kind of Eliason point flux analysis. So in short, we think that the inverse cascade is related to the wave mean flow interaction. So this is how we do it. So for the kinetic energy, you could decompose it in decompose the mean flow, the kinetic energy of the mean flow into a wave mean flow interaction here and a mean flow interaction here. So without going into a lot of details, so this is what we are claiming here. So in the lower stratosphere, so this is the wave mean flow interaction, the EP flux contribution, and this is the T0 term, which is the pump that we see earlier in the lower stratosphere. So we could see that these two values are pretty similar, and we could see that these two values are pretty similar too. So we think that the little bump in the transfer in the mean flow may actually comes from the wave mean flow interaction here. So I don't actually have the time, but I don't know if I'm going a bit too fast, but in summary, the horizontal kinetic energy spectrum for the aggregated simulation in the upper troposphere is steeper than the non-aggregated case. And the divergent kinetic energy actually dominates the horizontal kinetic energy spectrum in the lower stratosphere. In the upper troposphere, energy is mainly gained from the buoyancy flux and mainly lost from the vertical flux. And downscale energy transfer is found in the upper troposphere, and numerical dissipation is the main source of energy loss at small scale. And in the lower stratosphere, energy gained from vertical flux, and it is bound by the loss from buoyancy flux term, the transfer term, and dissipation. This time we see inverse energy transfer in the lower stratosphere, and we think that with the some point flux analysis, we think that the wave meaningful interaction is responsible for the upscale energy transfer in the lower stratosphere. And this is the end of my presentation.
Thank you very much, Donald. Are there any questions for Donald? Well, I can ask a first question. Donald, do you have a relatively straightforward explanation for the differences in energy fluxes between the aggregated and non-aggregated cases?
What do you mean?
Well, like that plot there, for example, showing in the upper troposphere very substantial differences in the
you mean this plot, or?
Well, the pair of plots. You've got non-aggregated on the left and aggregated on the right, and they're showing quite different behavior, particularly in the upper troposphere. Do you have a simple, straightforward explanation for what's going on there?
You mean this plot? You mean here, or the?
You don't pick your plot. You're showing very different behaviors for the aggregated case and the non-aggregated.
I think mostly the aggregator one, we could definitely see that, for example here, actually this responsible to corresponds to the size of the convective core. So that's why we could see that it's more energetic here. If you go back to earlier, you could actually measure the size of the convective core, and you could actually see that.
But is that entirely responsible for the change in the spectral slope?
I think so, yeah.
Okay.
Yeah.
You're sort of lifting up the low frequency end. Okay. Are there any other questions for Donald? Amine, do you want to?
Yeah, I wrote it in the chat. I am curious to know what was the logic that you categorize the atmosphere to these two categories. I might miss
Oh,
it.
no.
You explained it. Sorry if I missed it.
So there was one plot that I didn't show. So I have a temperature plot. I have a temperature plot that shows the changes in temperature when you reaches to the tropopause. So I didn't show it here, but essentially that tells me how I distinguish like the upper troposphere and the lower stratosphere. Yeah, the tropopause is around 12 to 13 almost like kilometers high. So yeah, I think this is what you're asking.
Is it a specific reason that you look at these two altitudes separately?
Oh, so it's also because like a lot of people in the literature, when they're looking at the energy spectrum, they separate it into like lower troposphere, upper troposphere, and lower stratosphere. And as it kind of makes sense here too, because there are different mechanics responsible for like in different regions. So for example, in the upper troposphere here, we could see that buoyancy actually dominates here, but in the lower stratosphere, we could actually see that vertical flux actually responsible for the vertical energy gain. So we think that in the lower stratosphere, wave is the main thing that we're looking here at. And we could also see that the decay is really strong here. So we think wave is the main thing in the lower stratosphere, and in the upper troposphere, the latent heat flux and stuff like the buoyancy flux are mainly the thing responsible here. So I think this is the logic behind.
Okay. And I think, again, we've come to the end of our time here. And in order to give people time for a bit of a break between sessions, I'd like to thank all of our presenters again. And just remind people that we have our second session of Atmosphere, Ocean, and Climate Dynamics in just under 20 minutes, starting at 1:55 Pacific time, and that would be then 4:55 Eastern, and people in other time zones can figure their times out. So again, thank you everyone for participating. And again, thanks very much again to Shahui for assistance with this session, and we'll see you all in just under 20 minutes for the second session. Thanks.